Tan Chen Hao over here, and today I'd like to share with you a method about thinking about permutations and combinations on a circle. This is a method that I think is much easier to think about and count in more complicated scenarios. So what is P and C on a circle? We are often given the typical question of 5 people in a circle on, let's say, some seats. So we have 5 people on a circle, and how many ways are there to arrange them? So the method that is taught, I believe, in school is 5 factorial over 5 equals to 4 factorial. Now what is the logic behind this division? The logic behind this division is that we first arrange the 5 people on a line. So for example, we arrange them A, B, C, D, E. How many possible ways are there to arrange all of them on a line? There is 5 factorial ways. So there is 5 factorial ways to arrange in a line. But in a sense, we have overcounted. Why have we overcounted? It's because we have, in these 5 factorial ways, among them is, let's say, E, A, B, C, D. And another one of them is D, E, A, B, C. Another one of them is C, D, E, A, B. Another one of them is B, C, D, E, A. And yeah, and then there's more. For example, A, C, B, D, E, and so on. So E, A, C, B, D. So why did I draw this line over here? Is because it separates the cases. So as I said, there are 5 factorial ways to arrange 5 people in a line. However, because we are in a circle, over here there is like a wormhole that joins this part of the universe with this part of the universe, right? So if you arrange them as A, B, C, D, E in a circle, then it's equivalent to arranging them as E, A, B, C, D in a circle, because it's just a rotation of the 5 people. And it's also, and these two cases are also equivalent to D, E, A, B, C, also equivalent to D, C, D, E, A, B, also equivalent to B, C, D, E, A. Because if you put the 5 people in a circle, A, B, C, D, E, this way of arranging the 5 people in a circle is, it all corresponds to these 5 cases, because you can rotate the circle. There's rotational symmetry. So because we have counted 5 factorial ways to arrange people in a line, and we have overcounted them by a factor of 5, meaning that for every valid arrangement, for every valid arrangement on a circle, it maps to 5 valid arrangements on a line, because we have overcounted, in a sense that one arrangement on the circle corresponds to 5 arrangements in a line. We have to divide this 5 factorial by 5, and hence we get 4 factorial. So yeah, so in essence, why do we take 5 factorial and divide it by 5? It's because for every arrangement on the circle, we map it to 5 different ways of arranging the people in a line. And these 5 different ways of arranging people on the line, they are equivalent to each other. So we have overcounted by a factor of 5, and hence we need to take 5 factorial, which is the number of ways people can arrange on a line, and we need to divide it by 5, which is the factor we have overcounted by over here. Okay, so that is one way of thinking about arranging 5 people in a circle. However, I would like to propose another method of thinking. So this is the other method 2, and I believe this method is easier to apply in other more complicated scenarios. So instead of first taking 5 factorial, which is the number of ways people can arrange in a line, and then dividing it by 5 later, instead of doing that, we first fix one guy. So 5 people. So first step is to fixate on one guy. In this case, for example, we fix it on A. Okay, then if for every arrangement on a circle, we ask the question, where is A located at? A is located at this position. So for every arrangement on a circle, for every arrangement of these 5 people on the circle, we map it to an arrangement of 5 people on a line, and we map it to the arrangement on the line where A is always in the first slot. Now you realize that this is a one-to-one correspondence, because for each arrangement of people of the 5 people on circle, there is one arrangement of 5 people on line with A being in the first slot. Right? So if we fix A over here, and then if we rotate it, A is still going to be mapped to this first slot. So in essence, since there's a one-to-one correspondence between the people sitting in a circle and the people sitting in a line with A being in the first slot, then we only need to count the remaining people, how many ways are there for them to fit in the remaining areas, which is just 4 factorial. So you see that we have reproduced the same answer, but with a completely different way of thinking. Instead of previously overcounting the 5 factorial number of ways to arrange in a line, and then realizing that, hey, for each arrangement in a circle, there's 5, it maps to 5 arrangements on the line, and then needing to divide by 5 to get 4 factorial. Instead of doing that, we immediately construct a one-to-one mapping from the 5 people on the table in the circle to the 5 people in a line by ensuring that A is the guy in the first slot. And in so doing, we only need to count the remaining slots, how many ways are there for people to fit in the 4 slots, and that is just 4 factorial. So with this new way of thinking, let's try to do this question. So there's 7 boys and 3 girls sit in a circle. How many ways are there to arrange such that for between every girl there is at least 2 boys? So we have 10 seats, right? So we first choose, let's say we choose somebody to fix it on. So we choose girl 1 to be in the first seat. So girl 1. Now how many other ways? So now that I fixed the girl 1 in the first seat, the only question remains to ask is, how many ways are there for the remaining 2 girls and 7 boys to sit in the other 9 seats? So there are 3 possible cases. Number 1 is this girl 1, and then we leave 2 seats for the boys, and then another girl, and we leave 2 seats for the boys, and then the girl. The other case is girl 1, we leave 2 seats for the boys, girl, then we leave 2 seats for the boys. We leave 3 seats for the boys. We leave 3 seats for the boys, and then go here, and then we leave 2 seats. And the third case is girl 1, we leave 3 seats for the boys, girl, then we leave 2 seats for the boys, and then girl, and we leave 2 seats for the boys. So this is 2, 2, 3, 2, 3, 2, and then 3, 2, 2. So you see that there are 3 possible arrangements, and for each case we need to count the number of valid seating arrangements. So for the first case, since girl 1 is already fixed here, the remaining 2 girls and 7 boys have 7 factorial for the boys, and then for the girls there's 2 factorial, right? For case 1, 2, and 3. For case 1, there's 7 factorial and 2 factorial. For case 2, there's then also 7 factorial times 2 factorial. And for case 3, there's also 7 factorial times 2 factorial. So the answer is just 7 factorial times 2 factorial times 3 because there's 3 different cases and you add all of them up. So this is the final answer, which is 30240, and that's the answer to this question. Now you see that by choosing the one girl to be always seated in the first seat, it's much easier to think about counting the remaining people than if we had to say that like okay, we first arrange them, then there could be, let's say, boys here, then girl here, and then boy, girl, and then boy, oh wait, I'm missing one girl, so let's say like that. Hold on, 1 2 3 4. It's much okay. My point is, it's much easier to think about it in this suggested way by fixing one of the people in the first seat instead of thinking like that, and then like you need to think how many ways are there for them to permute. But once they permute, would it divide by 10 or something? Yeah, my point is that this is a different way to think about uh, people sitting in a circle. Yeah, instead of counting them in a line first and then dividing by some permutation, we count them in we count them by fixing one guy to be in the first slot, and because there's a one-to-one mapping from the people in a line with one guy fixed in the first slot as to the number of people in a circle, because there's one-to-one arrangement, we just fix one guy in the first slot and then we count the remaining people. So I hope that this is a method that you'll find useful in your exam. And yeah, if you did, please leave a like and leave a comment as well. Yeah, bye.